Everybody, welcome back. This is Mr. Christopherson. This is day 3 of our e-learning experience. The topic for today is electrolytes and cold packs. I needed to do a little bit of review of solubility. I mentioned it in yesterday's lesson, but I didn't necessarily show you graphs, and I'd like to show you that graph today if I can. Then later on, we'll go through and see what's on the calendar, some extra videos for you to watch, a little fun demo for you to watch, and I think it'll all make sense to you today. So let's get right into our PowerPoint presentation. So again, I'm reviewing a little bit from yesterday the effect of temperature on solubility. And for most substances, what we see is we're looking at a graph here of solubility, that's grams of solute per 100 grams of water as compared to the temperature. And we notice for potassium iodide, as the temperature goes up, we get more potassium iodide to dissolve. Sodium nitrate, higher temperature, more to dissolve. Potassium nitrate, same pattern. Sodium phosphate, same pattern. Sodium chloride has very little temperature dependency. As a general rule, what we would say is, as the temperature goes up, solubility of solids go up. Now for gases, it's a little bit different. The unit here we have is millimolarity. The unit's unimportant versus temperature. It's how much gas is dissolved over temperature. And if we look at these gases here, methane, oxygen, carbon monoxide, and helium, as the temperature increases, we get less and less and less of those gases to dissolve. And this is what happens when you have carbon dioxide in your pop, and your pop or carbonated beverage warms up. It goes flat as the gas comes out of solution. So the higher the temperature, gas is less soluble. That's what that subtle, gigantic arrow is trying to tell us there. Okay. So in general, for most solutes, higher temperature, higher solubility. Gases, just the reverse. All right. We could go through solubility rules because of the nature of this shutdown, the time we have together. I'm not holding you accountable for memorizing these solubility rules or even utilizing them. We'll stick with our solubility table if we need or have any questions about solubility. This is just another graphic to help you if we were going to do that. But again, we will use our solubility chart to determine solubility. We won't memorize any of that. So that's a little bit of review from yesterday. And now what I want to talk about today is electrolytes. Now, if you've ever done any sports in your life, maybe it's really hot, you haven't hydrated enough, you haven't eaten enough, and you start to cramp up. What you're experiencing is an electrolyte imbalance. So in order for an electric current to flow, you have to have ions present. And if you've ever really done a lot of physical activity, you start to perspire and sweat, and if you taste your sweat, it's salty. You're losing sodium and chloride ions. It's those sodium ions that conduct an electric current. So what we're looking at is a simulated demonstration where we have a battery with some power coming through it, hooked to a light bulb, hooked to a piece of metal stuck in water, and then another piece of metal stuck to the other end of the light bulb. Now this is perfectly safe to do, as no electricity will flow through the gap because it's pure water. There are no ions to carry an electric charge. If, though, you sprinkle some salt in the water, the salt will dissociate into its ions, that is the positive sodium ion, the negative chlorine ion, and those ions will allow or carry the electric current from one electrode to the other, and the light bulb goes on. Many things can be electrolytes. We'll discuss those things here shortly. So in my first solution, I have a non-electrolyte, and notice the light bulb doesn't go on. An example of a non-electrolyte is any molecular compound that does not dissociate. Let me give you an example. Sugar. If you drink sugar water, pop, you will cramp up very quickly because it's not an electrolyte. You need to have ions present, and those would be ionic compounds, not molecules. A weak electrolyte, and we'll have to discuss this a little bit further, it is an electrolyte. The bulb goes on, but only to a small extent. And it's hard for you to see, but if you look right inside the beaker, I have three molecules here, three compounds, and only one of the three has dissociated. So only 1/3 of it is carrying the electric charge, so the light bulb doesn't go on very much. In the last example, all three of the compounds have fully dissociated, and so we call this a strong electrolyte. Now, to be a weak or strong electrolyte has everything to do with the nature of the material. We don't determine that. An example of a weak electrolyte would be something like hydrofluoric acid. The fluorine is so highly electronegative, it doesn't let go of the hydrogen, so it stays together even in solution. It does not dissociate very well. A strong electrolyte would be like sodium chloride or hydrochloric acid, where when you put it in water, it dissociates nearly 100%, and the light bulb goes on very brightly. So an electrolyte is a solution that can carry an electric current. In the first example, I have a strong electrolyte, sodium chloride. You can see all of the sodium and chlorine compounds have fully dissociated and have lots of ions free to carry the electric current. So notice when we write this equation, NaCl, AQ means aqueous, there's a one-way arrow making a sodium and chloride ion. That's what you expect, a single arrow for a strong electrolyte. In the second example, we have hydrofluoric acid. This is a weak electrolyte. You can see I have 5 HFs in solution, and only 1 out of the 5, or 20%, dissociated and made the ions. And because only 1/5 are working, the light bulb glows, but not as bright as in a strong electrolyte. Notice when I write this dissociation, the HF has a double arrow, meaning some of it breaks down to H plus and F minus, but some of it returns to HF. And that's how we write a weak electrolyte, with this double arrow. And a non-electrolyte, these are like molecules like sugar. These are covalently bonded. They do not dissociate, they do not make ions, and they do not conduct an electric current. And the light bulb simply doesn't go on. If you were looking at the molecule of sugar, there it is. It's a very, very big molecule, and it does not dissociate at all. Now, sports drinks like Gatorade and Powerade do have a lot of sugar in them, but what makes them electrolyte is the fact that they contain salts. The salts conduct the electric current. The sugar is added for a couple reasons. Number one, it masks the saltiness of the drink. No one would drink a glass of salt water as an electrolyte, although it would work. Secondly, sugar is a good source of energy when you're doing a high energy sport. They make different electrolytes. Some of the drinks are used before you exercise or while you're exercising that have higher sugar. Some are used after that have lower amounts of sugar. And one thing I want to talk about was what can happen if you have an electrolyte imbalance. So this is Korey Stringer. He was a football player for the Minnesota Vikings, and he collapsed during practice when it was very hot, wearing full pads from excessive heat, and he died the following day of heat stroke. Unfortunately, this is all too common for athletes that practice in very bad weather. You know, as coaches will often use the phrase, play through the pain, fight through the pain, ignore the pain, and all these things. I would suggest listen to your body. If you're feeling lightheaded, if you're feeling dizzy, if you're having problems seeing, you don't play through that pain. You tell the coach you need to be cooling off, to go see a trainer. If your internal body temperature gets too warm, 105, 106 degrees, what happens is we have lipid bilayers. They're oils that coat our organs, and those literally melt. And at that point, you have organ failure. And even if you cool off after that, you're going to have permanent damage to your body. So heat stroke's a very, very serious issue. It's more serious, I would say, for football players than for cross-country runners. Cross-country runners are wearing shorts and not pads and helmets. Football players have pads and helmets and tend to be a little bit bulkier, larger individuals than the people that run cross-country. The solution for this is on hot days to have practice early in the morning or late in the evening when the temperatures are cooler. And make sure you take hydration breaks. Don't practice with full pads or helmets. These are prudent things to do to prevent heat loss and heat stroke. We have to have the right electrolyte balance in our body. If not, our body doesn't do very well. Little children, babies in particular, don't weigh a whole lot. If they have diarrhea or throw up, it can be a relatively large portion of their body mass, losing lots of electrolytes, which can become very serious very quickly. I've listed a few different type things here. One is the sodium ion electrolyte. There's a normal range in your body. If you have too much of the sodium, we say you're hypernatremia. Natremia refers to the name of the element sodium, comes from the Latin natrum. And what your body will do is you will tend to excrete excess urine to try to get rid of that sodium because it's water soluble out of your body. That's what your effect will do. Now, if you don't have enough sodium in your body, you will end up having, as it says, symptoms of dehydration, diabetes, low blood pH, vomiting, and diarrhea. This is what happens when marathon runners drink too much water. The phrase is they get waterlogged, but they drink so much water, it dilutes the sodium that's in their body to a too low of level. That's what the word hyponatremia means. And the body's response from drinking too much water is to get rid of that water through vomiting or diarrhea. Potassium, we get a lot of potassium in our bananas. You don't need very much potassium in your body, far less than the sodium, but you can see it can have problems if it's high or low. We'll talk later about the hydrogen carbonate or bicarbonate ion. It's a very important ion in your body. We'll talk about that in a later lesson related to conditions called acidosis and alkalosis and what that means. If you're not feeling well and you're exercising a lot, sometimes drinking water is not enough. Drinking pop is definitely not the right solution. You generally want to get to shade. You want to be thinking about having some electrolytes. They make popsicles that have Pedialyte for little children. You can drink those or Gatorade, whatever, and that will certainly help restore your electrolyte imbalance. If an EMT gets called to a scene and they see an unconscious person, the two things they're probably going to think about are, number one, a drug overdose, and they might give the person Narcan to see if they can return them to a normal balance. If that doesn't work, then they're going to probably immediately start an IV. And an IV is nothing more than an electrolyte solution, trying to restore the electrolyte balance to that individual. Let's talk about the effect of salinity or salt on cells. I have a cute little picture of a snail. I have lots of hosta plants in my backyard, and they like to grow in shade. And unfortunately, when it's really wet, the snails and slugs come out from under the grounds and eat my plants that I don't want. Now, you can do several things to prevent these snails and slugs from attacking your plants. You can buy different poisons to sprinkle out, and they will eat and die. I don't prefer that because other animals like cats or other things could eat that poison as well. So I prefer not to do that. You can, and this is interesting, you can take a copper wire and twist it around the base of the plant. And so if this is the plant, it has a copper wire around it. As the slug goes up, when it touches the metal wire, it gets a small electric shock. It's like a little electric fence. And then they crawl back down and will attack another plant. I kind of like that option. If I'm getting really a lot of slugs, I'll go out there and I'll pick them off by hand. It's kind of gross. And I'll put them in a bucket and I'll put salt on them and they'll shrivel up and die. It's a little mean, it's a little gross, but I do like my hostas. Now, let's talk about what happens to maybe older people. Think of your grandparents if they have a heart condition. They have to watch how much salt they have on their diet, because what can happen is their heart can swell and their ankles can swell, and that can cause congestive heart failure. So how does this all work? Well, let's look at this diagram here. This is called an isotonic solution. Iso, think of an isosceles triangle, it's two sides the same. Well, in this case, the salt represented by the yellow dots and the water, the blue dots, are equal concentration inside my little pink cell and outside my cell. So the salt and water are able to, at least the water is able to move inside and outside of the cell. The salt's sort of stuck in there because it's too big to get out. And so because it's an isotonic solution, the salt is the same on the outside and inside of the solution. There's no change. This is like you using contact solution or eye drops in your eyes. As long as it has the right salinity, that salt content, it doesn't burn. If the salt was too concentrated or too dilute, it would irritate your eyes quite a bit. In the middle example, I have a hypotonic solution. Hypo, remember, means low. So on the outside, I've taken my cells and I put it in fresh water, and on the inside, I have salt. So what happens is the cell doesn't really have control over this, but Mother Nature likes a balance. So to try to make the inside of the cell less salty, Mother Nature pushes water from outside the cell into the cell, and the swells swell up. And this is what happens if you take too much salt in your diet. You get congestive heart failure. Your heart will swell. Your ankles will swell. And that can be very, very serious. And then they'll have to put you on diuretics to get rid of the excess water. The process, if it's too extreme, causes a condition called hemolysis, where the cell literally splits or bursts as too much water goes in. Lysis means to split something. In the last case, we have a hypertonic solution. Hyper means high amount, and what is happening is there's too much salt outside the cell, and the cells don't have little hands to wipe off the salt. So what happens is the cells push water out of the cells, and as they push water out, they kind of shrivel up. The term for that is crenation. And this is what happens to the little snails. When you put salt on them, their little bodies crenate, and they die in that fashion. Finally, I just want to show you slides of what these actually look like. These are red blood cells, or cells in dilute salt solution. This is what they should be looking like. That little dip in the middle looks like a tasty donut. And then you have cells in distilled water. And again, at this point, in the first one, it's isotonic. It's the same concentration inside and outside of salt. And the middle one, this is hypotonic. We've got too much water on the outside, too much salt on the inside, and water goes into that cell, causing it to plump up and potentially burst. And in the last example, we have a hypertonic solution, way too much salt on the outside, and so the water inside the cell pushes out, and the cells crenate and shrivel up. So isotonic, hypotonic, and hypertonic. These are all different types of solutions. I hope you have a slightly better idea of what electrolytes are like. I'm now going to ask that you go to the actual website, and let me see if I can find where we're at here, the calendar. So what I've left for you is another video with Professor Dave talking about electrolytes. I'd like you to watch that. Then as another chemistry teacher, Tyler DeWitt, is going to show you what happens when stuff dissolves through some animation. Again, these are very good videos to watch to get a little bit more explanation about what we're talking about. And then finally, there's a fun little demonstration where he's going to take two chemicals, put them together. They're going to get very, very cold, so cold that it freezes to the table. Just an example of an endothermic chemical reaction. For homework, I want you to read the article, Don't Sweat the Small Stuff, and it has to do with electrolytes, obviously. And then there are some questions that you will need to print off and answer as well. Probably the PDF will be the best way to go for that. Good luck. Please try to keep up with your studies of chemistry. Send me questions if you have them. I'll try to respond in a reasonable fashion. Best of luck and stay healthy. Take care. Bye-bye.